Okay, this is the final video that corresponds to the second live class for Physics 100. And last time we were talking about the quantum physics of something like a bouncing ball. So a ball that bounces off the ground, rises to some height, goes back and forth. If you look at the wave function for that, right, you solve the Schrodinger equation to find what is the wave function that describes such a system, and then use that to determine the probability distribution, you see that it has some features that make a lot of sense, right? At low altitude, it has a short wavelength that corresponds to a high kinetic energy. At high altitude, it has a much longer wavelength because the particle is moving more slowly, and also the probability is generally higher of finding it up there. And there's some wavy stuff happening in the in-between regions. We also see this exponential tail at high altitudes where the particle has some appreciable probability of being found at a height higher than the maximum height it should be able to reach for the energy it's been given. And the question we asked at the end of the last video is, how do we show that that's a real thing? How do we know that this is something that happens? The answer is we can't really do that with a ball thrown up in the air because gravity just keeps going and going and going. The potential energy just keeps increasing and increasing as we go up. But we can do this and see the reality of this physics if we look at a different kind of system, one where the potential energy is just a thin barrier, right? So we have some region of space in which the potential energy of the particle is quite high, right? And typically we draw that as a square thing, it just suddenly comes on and suddenly cuts off. And that region is relatively narrow. And outside that region, the potential is very low, right? So in this case, we can have a particle that comes in with some total energy that is lower than the height of that barrier. Now, classically, you would say, well, if it comes in, if it hits that barrier where the potential energy goes up to higher than the total energy of the particle, it has to stop there and turn around and go back. But in quantum physics, right, we saw that this instead turns to a decaying exponential, an evanescent wave that exists inside that barrier region. And if that barrier region is fairly thin, there can be a reasonable probability that the particle shows up on the far side because that wave function won't have decayed all the way to zero by the time the potential energy comes back down. So what does this look like? Well, we have a situation where we have three kinds of waves that we have to deal with. We've got an incoming wave that is on the left side of the barrier. That reaches the barrier. It has a total energy that's less than the height of the barrier. So there's going to be a lot of the particles are going to reflect. So there'll be a reflected wave going back in the opposite direction. And then there's a transmitted wave on the far side that has some probability of just continuing on. The particles show up on the other side and keep going. Inside the barrier, there's this evanescent wave. Right? There is a wave that's a decaying exponential kind of thing that exists inside that barrier, and that doesn't get all the way to zero before the potential energy comes back down. What do we have to do with this? Well, the process for finding the wave function here involves a ton of algebra, really. We have to match the wave function at each of these boundaries. So the sum of the incoming wave and the reflected wave has to be equal to the evanescent wave right at the start. And then the evanescent wave and the transmitted wave have to be equal to each other right at the end of the barrier. So those two boundary conditions have to be met. We also need the slope of the wave function to be continuous across both of those things. So they have to come in with matching slopes. Whole bunch of algebra to this. The key result of this is that you end up with a probability of transmission. You end up with an amplitude for that transmitted wave that isn't zero. Right? There is some probability of getting through, even though the total energy of the particle is less than the potential barrier that it would have to go above. And classical physics says that it should 100% bounce off that and go back the other way. What does this probability look like? As I said, it's a ton of algebra, but we can skip to an answer that has sort of the form that you expect. There are some terms that depend on the energy compared to the potential out front. And then there's this exponential. There's an e to the -2 kappa times L. L is the thickness of the barrier, Kappa is this evanescent wave number that we talked about when we talked about these decaying exponentials. It's the square root of 2m over h bar squared times the potential energy, the height of that barrier, minus the energy of the particle that comes in. All right. So this thing says this is exponential in that product kappa times L. Right? So if I make L bigger, the probability of transmission drops off exponentially. If I make that kappa bigger, the probability of transmission also drops off exponentially. All right, so this probability can be very, very small. And in fact, this particular expression is an approximation that only works if it is in fact very small, if the energy is much less than the height of the barrier. But this works pretty well for that. And it gets you the right idea that there is an exponentially decreasing probability of finding the particle on the far side of the potential barrier. So is this thing a thing that really happens? The answer is yes, and it's actually a terrifically useful thing. If you ever heard of a scanning tunneling microscope, the tunneling that's in there is this phenomenon of tunneling, of particles showing up on the far side of a barrier they don't have enough energy to cross. Right? So it's a scanning tunneling microscope. You have a pointy metal tip. You bring it very close to a surface. You put a small voltage between the tip and the surface, and there's some current will flow across the gap, the air gap, not because the air acts like a reasonable resistor, but because of quantum tunneling. Because the air gap poses a very large potential barrier for these electrons to cross, but there is some probability that they will nevertheless make it across there because of this quantum tunneling. And the amount of the current that you get drops off exponentially with the distance, right? So dropping off exponentially means it changes very, very fast. Fast enough that if you change the height of the tip above the surface by about the diameter of an atom, that will reduce the current that's flowing by about a factor of 10. So very dramatic reduction in current for a very small change in height, right? Small enough that it can pick up single atom bumps. Right, and so this is a device that you can use to measure materials atom by atom, and to make these cool pictures that you see here of these lumps that represent single atoms of one type sitting on top of a surface of some other type of atoms. So this is a tool that's used all the time now in physics, studying materials at the smallest scales. There's another really great example of this physics, and that is the sun. Okay, how does the sun shine? Well, these days, kids in grade school learn that the sun shines by burning hydrogen into helium. Right now, it's not literally burning like rocket fuel. It's burning in the sense of nuclear fusion. We take the two nuclei of hydrogen atoms and we throw them together. And if they get close enough together, they can stick. One of them turns into a neutron in the process, and it releases a little bit of energy. And if we take two of those things, it's called a deuteron, a proton plus a neutron bound together. We take two of those things, we can stick those together. And when we do that, we end up with the nucleus of a helium atom, 2 protons and 2 neutrons. Right? Both of these steps release some energy. That energy goes into heating the stuff that's in the sun and keeping it hot. And because the sun is very, very hot, it glows and it emits light, and it makes for lovely days. Some of the time. Not so often in Schenectady, but what can you do? Now we can look at this and say, well, there's a potential barrier to this happening, right? These two positively charged protons, right, that are the nuclei of the hydrogen atoms that we start with. We throw those together, they repel each other. There's an electrostatic force pushing them apart. There's some energy associated with that. There's an energy barrier that they have to overcome. And we can ask, well, how much energy do these things have to have as we throw them together for them to get close enough that they would stick and form a deuteron? You can do that. You can convert that to a temperature. This is actually going to be on the homework for this class. And that temperature turns out to be something like 15 billion degrees Kelvin. Right? So 15 billion Kelvin is the temperature that the sun would need to be for these two protons headed straight at each other to come together and collide, right? And get close enough that they could stick and undergo nuclear fusion. And we also know what the temperature of the sun is. We can measure the temperature of the surface of the sun very directly. We can model what's going on inside it. And the temperature of the sun is about 10 million Kelvin, right? Now 10 million is not 15 billion, right? This is a factor of like 1,500 difference between these two things, right? The temperature of the sun in the core of the sun is not nearly hot enough to throw two protons together fast enough that they should get close enough to stick and undergo nuclear fusion. How does the sun shine? The sun shines because of quantum tunneling. Right? As these two protons come together, there's an energy barrier that's keeping them apart, but there's some probability that the proton that's on its way in can just tunnel through that barrier, show up on the far side, because it's a quantum particle. Now, this probability is absurdly tiny, right? If you work out some simple approximations for it, it comes out to, depending on how you do it, 10 to the minus 30, 10 to the minus 40 even. The probability of this happening is really astronomically tiny. However, the sun is also absurdly huge, right? The number of protons that are rattling around inside the sun at this 10 million Kelvin temperature is so enormously large that even though the probability is ridiculously small, this happens very regularly, right? These protons really do quantum tunnel through this energy barrier. They fuse with each other. In the process, they release heat. And that's what keeps the sun shining and keeps this fusion process going on. So those are two examples showing that tunneling is a real phenomenon. Right. Now, the last thing we want to address here is, we want to talk in this module about this paper where they measure this in experiments with atoms. They do an experiment in a laboratory in Toronto where they see this quantum tunneling happening. And they measure how much time it takes. So how do you do this when you're talking about atoms? We can get a sense of what we're after here by looking at this approximation for the tunneling probability in the case where the barrier is very tall. All right, and the answer is we need this product of kappa times L to be smallish. It doesn't have to be zero. It doesn't have to be incredibly tiny, but we need it to not be really big, right? So if we want there to be a reasonable tunneling probability, something we have a chance of seeing in the laboratory, we need that product to be fairly small, which means we need a fairly small barrier, and also we need that kappa to be a small number to be correspond to a long wavelength, right? If we want to have atoms that have a long wavelength, this long evanescent tail, we need them to be moving very, very slowly. And that's going to be the subject of the next live class. The next set of video lectures is going to be how do we get atoms to be moving slowly enough that we can start to talk about seeing this quantum tunneling very directly with big, heavy things like atoms moving through barriers that are, a micron thick. That's fairly substantial on the scale of an atom. That's going to be the subject of the next lecture. That'll be the subject of the next set of videos. So stay tuned for that, and we will see you there.